Hello, this is Miss Dagenford, and I wanted to continue with the second large process in making a protein, and that would be translation. Now, before we do that, we want to make sure we introduce all of our key players. And so we want to go back to the idea that the transcription can make different types of RNA. Now, the one that we looked at was messenger RNA, and we're going to look at two more during the process of translation. Now, one of the key things to remember is that RNA is single stranded, and because it's single stranded, it can do a really interesting thing. Just like a big strand of sticky tape, it can fold back on itself and make kind of a tangled shape. Well, RNA contains these hydrogen bonds, and so remember the hydrogen bonds mean that the two strands can fold back. And so what you're seeing is a series of examples of RNA molecules that are twisting and folding and sticking together because they have complementary base strands that would then allow them to do so. This gets real interesting and crazy. Let me show you some of the different diagrams you'll see. Now, the one on the left is more of a schematic. It's as if you kind of lay down the piece of tangled tape and spread it out on the table to see where the tape is sticking together. And so you can see all of the lines represent hydrogen bonds, and we have these hairpins and loops. The loops are caused because they don't have anything to hydrogen bond to, and that ends up influencing its ultimate three-dimensional shape. So our RNA can create these very fascinating complicated shapes, and because RNA can hold on to things with their nucleotides, that can mean that they can do things with that. They can have catalytic properties, meaning they can help facilitate bonds being made and perform different jobs. And so that's what we're going to take a look at. So in translation, what we're going to see is transfer RNA. I totally forgot. So ribosomal RNA would be long strands of RNA that when they fold back create, and there's multiple parts of RNA. And so when they do, they kind of create this big super complex of RNA, and then some proteins are in there as well. And that makes up a ribosome. So that's one type of RNA that would be ribosomal RNA. So ribosomal RNA is made of RNA and protein, and that creates this very large three-dimensional structure. The other one that we're going to learn about would be transfer RNA, and transfer RNA also has our shape because the tRNA can fold back. Now, different books have different ways of showing this. So again, there's a schematic two-dimensional view that shows the tRNA folding back and creating this hairpin and loop structure. All of these would be the hydrogen bonds. In a more three-dimensional shape, it kind of, to me, looks like an upside down capital letter L, or you can think of a capital letter F without the little stem here. But it's still showing that one end has these open nucleotides, and then the end down in the middle has another set. Now, the two ends are very, very important. One end is the anticodon, and that's going to complement base pair with our codon. And then the other end is going to connect to an amino acid. And the thing to remember, or the thing to know about tRNA is the specificity of the anticodon to the codon also applies to the amino acid that it brings. In other words, the anticodon that matches to the codon is also going to bring the correct amino acid. So the anticodon for methionine means that tRNA is only going to bring methionine amino acid. This tRNA molecule with the correct anticodon is only going to bring asparagine, and this tRNA molecule with this anticodon matching that codon is only going to bring histidine. So tRNA ends up acting like a translator. So think transfer RNA with its anticodon acts like a translator. Think of the T's, that really helps me. So tRNA, anticodon, translate. So specific tRNAs will bring the right amino acid because the anticodon matches with the codon. So there's a lot to this process. Let me illustrate the ribosome, the large brown structure you see, and then the areas of the ribosome. So what do we need to make a protein? We need the code, we need the mRNA, we need the code breaker, the tRNA, so the anticodons fit the codons, bringing the correct amino acids. And then we need a place where everything comes together, and that space will also facilitate the bonds that will be made. And that's going to be the ribosome. So the ribosome, that large brown structure, contains docking spaces for tRNA. And then it's going to act as the enzyme. It's got catalytic function that's going to connect those amino acids together. Now, let's real briefly remember where all of this is happening. In prokaryotes, this is happening in our cytoplasm. And so remember, transcription and translation can be happening at the same time. So as a gene is getting transcribed, there could be ribosomes on that growing mRNA strand already translating it. So prokaryotes don't mess around. In eukaryotes, we have free-floating ribosomes in the cytoplasm. And while they're all going to be found in the cytoplasm, some of them just stay in the cytoplasm and make their proteins. And those are going to be for proteins that work in the cytoplasm, like glycolysis, enzymes, or cytoskeletal proteins. They're working in the cytoplasm. They don't need to go anywhere. However, if it's a protein that's destined for secretion or the membrane, and we discussed this a few months ago, if it's going to go there, it needs to dock to the ribosome needs to dock to the rough ER, where it's going to finish translating the mRNA, and then that protein is going to be taken to the right place. So here we see our ribosome. So let's go around and make sure we see everything. First, we see the mRNA strand that's going to be, here's the mRNA strand that's going to join onto the small subunit of the RNA, and then the large subunit will come over as well. You have three areas on the ribosome: E site, the P site, and the A site, and they can easily be remembered because the E site is where the empty tRNA exits. Then you have the P site where the growing polypeptide is, and then you have the A site where the new tRNA comes with a new amino acid. So what you're going to see is that the tRNAs that have the correct anticodon codon match, they're going to bond, hydrogen bond, and that's going to allow the ribosome to make a peptide bond. So the basic idea is the ribosome is going to travel down the mRNA strand, the tRNAs float up. If they don't match, they're just going to drift off again. There's no hydrogen bonds being made. If there is a match, then the hydrogen bonds allow it to just temporarily stay. The ribosome is then going to make a peptide bond between them, and then the whole thing shifts down. This slide, I'd like you guys to take a moment and practice. All right, let's go on. Now, this one I'm going to have to go back to the layout. Now, I'm just going to show you 3 times what happens. So, to start the translation process, we're going to have our mRNA strand with our first codon, AUG, and we're going to bring in the tRNA strand. And I know they kind of look like demented Christmas trees. And this tRNA is going to match up, and we know they're not going to perfectly align. Sorry about that. But this codon is going to match with the anticodon, and now we have the right amino acid, methionine. Now, that's how we initiate. And virtually all organisms start with methionine and have the same code. So we see this as a universal, nearly universal code. Then we want to bring in the next tRNA, and that's going to be the one that matches with our codon. So we've got CCC, the anticodon is going to be GGG. Now, it's at this point that the ribosome can make a peptide bond, and my amino acids, I need to make that longer a little bit. So we're going to make a peptide bond between these two. Now we've made the bond, so let me ungroup these. And as we make that bond, the ribosome is going to translocate. It's going to move over. And notice what that does. We have an empty A site. Now these amino acids are bonded together, so we can get rid of this tRNA molecule, and this methionine is now connected to the proline. Well, I want you to see if you can predict what's going to happen next. And so what we're going to have is the next, and I didn't have a chance to make the anticodons, so we're going to make the next match, which is going to be aspartate. And again, the right codon and anticodon is going to fit, and the ribosome is again going to make our peptide bond. And again, I need to ungroup these so I can show you the next step. But I want you to be thinking what's going to happen next. And so you should have said the ribosome moves over again. And now we free up another A site. The tRNA that is now empty can leave. These can go back and pick another amino acid up. But in the meantime, notice I've got 3 amino acids all kind of tied up, and we're building our amino acid. So last question, I want you to think, okay, how are we going to add this arginine to our growing strand? All right, so think about that. That'll be your last question on our Edpuzzle, and hopefully that helps you get an understanding of translation.